Okay, so welcome to week 10 of the problem solving session. So this session was postponed. Earlier it should be on Friday, but due to some unavoidable circumstances, it is postponed for today. So we'll discuss problems based on week 10 lectures that are being uploaded in the NPTEL course. Okay, so my screen is visible to all. Okay, so I hope it is visible. Fine. So let's start with problem number 1, where we are given a closed loop system with open loop transfer function of s plus 1 divided by s square plus 7s plus 10. Find out the slope of the high frequency asymptote of the Bode plot. Okay, so in the week 10, professor has discussed problems on or lectures on Bode plot and some of the problems on Nyquist plot. So we will solve some problems based on these concepts only, Bode plot and Nyquist plot or polar plot. So the first question is based on Bode plot, where you are given an open loop transfer function. We are given g of s as s plus 1 divided by s square plus 7s plus 10. Okay, we need to find out the high frequency asymptote. First tell me how many poles and zeros this transfer function has. How many poles we have?
2 poles
So we have number of poles as
and
2.
1 0.
Yes, and number of zeros we have 1. Okay. Okay. And what is the type of this system? Is it type 0, type 1 or type 2? Do we have any pole at the origin?
No, ma'am.
So since we have no pole at the origin, so type of system is 0. So it is a type 0 system. Okay. Now since it is a type 0 system, okay, next what we need to find out the corner frequencies. So we have identified the number of poles, number of zeros, type of the system, and tell me about the corner frequencies. What are the corner frequencies of this system? For that, let's first convert this transfer function into the time constant form, right? So what is the time constant form? It is of the form of 1 plus st. So first let's try to separate the poles. So it will be, I think, s plus 2 and s plus 5. Okay, we can write it like this. The denominator we have separated the poles, and then in the time constant form it will be 1 plus s divided by 1 plus s by 2 and 1 plus s by 5 into 5. So it will be 10 into 1 plus s divided by 1 plus s by 2 and 1 plus s by 5. Okay. Now can you identify the corner frequencies?
Ma'am, will this 2 into 5 will be in the denominator?
Yeah, so it will be in the denominator, then finally this denominator will be the numerator. Okay.
1 to 5.
How, ma'am?
Let me show you then how we have converted into the time constant form. So we have 1 plus s. Okay, so we have the factor of 1, so we need, so t equals to 1 here. Here we have taken out s 2, so it will be s by 2 plus 1, and from here we have taken out 5, so it is s by 5 plus 1. Okay, now so this will be,
That's point one
oh
divided
yes,
by
yes, 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 right, right, so you are right, sorry. So here it will be in the denominator, right? Okay, is it correct now?
Yes, ma'am.
Okay, okay, thank you for this. Okay, so what are the corner frequencies? So corner frequencies are 1 by t.
125.
Okay, so t here is 1, 1 by 2 and 1 by 5. Okay, so the corner frequencies will be 1, 2 and 5, right? Now since we have everything in our hand, now let's draw the Bode plot. Okay, so we have corner frequency at 1, 2 and 5. I've just marked it. Okay, since this is a type 0 system, what will be the initial slope? If we talk about frequency less than 1, what will be the slope of the Bode plot or the magnitude plot?
0.
It will be 0, okay? Because the initial slope is contributed by the 0 at pole or pole at 0 or 0 at the origin. So since we have no poles or zeros at the origin, we will have a 0 initial slope. Okay, now we have a corner frequency at 1, and this one is contributed by the 0. Okay, then what will be the slope after that?
20
Plus 20 or minus 20?
plus 20.
Right, so it will be plus 20 dB per decade. Okay,
And 20 log of point 1 you have to consider or not?
sorry.
20 log of point 1.
No, we are not actually drawing exactly the magnitude. We are just sketching the asymptotes, just to know
Oh.
what will be the high frequency asymptote. What will be the slope of the high frequency asymptote? If you want to actually plot the magnitude plot, so you can calculate the frequency and mark the magnitude whatever it is at 1, 2, 5, at any frequency if you want. Okay, now what about at omega equals to 2?
Minus 20 decibel.
So we have a pole at this corner frequency, then it will contribute a slope of minus 20 dB per decade, right? And earlier we already have a slope of 20 dB per decade, and if we add a slope of minus 20 dB per decade, it will nullify its effect. So ultimately we have a zero slope, right? Okay, so it is a 0 dB per decade slope. And what about after corner frequency of 5? We again have a pole, so again it will contribute a
I
slope of
minus
minus 20 dB per decade.
minus 20 dB.
Yes, so again we will have a slope of minus 20 dB per decade. Okay, so this doesn't give you the exact Bode plot or the magnitude plot of the transfer function. This is just the asymptotic view, right? If you want to have a realistic picture, you need to find out the magnitude and then plot the exact magnitude with respect to the frequencies. Then you will get something of like curves, not these straight lines, right? So these are just the asymptotic plot. Now if I ask you, what is the slope of the magnitude plot as frequency tends to infinity? What will be the answer? If I increase frequency to infinity, what will be the slope of the magnitude plot?
minus 20 dB per decade.
It will be minus 20 dB per decade. So, if you were asked to find out the high frequency asymptote, it is nothing but the slope of the magnitude plot as frequency tends to infinity, right? So it is minus 20. Okay, any doubt?
Ma'am, in the assignment it is asked to calculate in the dB per octave. So how to convert it?
Okay, so in dB per decade, you increase the frequency by 10 times or 2 times.
10 times.
I think in the previous assignment I have solved this type of question, so you can go through it because directly I cannot give you the answer. So please refer to the previous session. I have told you how to find out the slope in dB per octave, right? In that you have to just scale the frequency by 2 times, and then you have to check what is the slope you are getting.
Ma'am, is there any way to convert dB per decade into dB per octave?
Any way to convert? Um, any formula if you ask me. So dB per decade is the denominator. So this x-axis is scaled by 10 times. Excuse me. Yes. Okay, you know how to calculate slope using, so slope is nothing but y by x, right? Hello?
Yes, ma'am.
So slope is nothing but y by x. So in y, what you have? You have 20 log of g at frequency omega 1, let's suppose, and you have another 20 log magnitude of g at frequency omega 2, let's see. And what you have on the x-axis, it is log of omega 1 minus log of omega 2. Okay, now
Yes.
so this slope remains same, and in that you have to adjust your x in the way that you get your slope in octave or decade. Okay, so by octave means your omega 2 by omega 1 will be 10, sorry, by is 2, and by decade means your omega 2 by omega 1 will be 10. Okay, so that means log of w2 minus log of w1 will be log 2 in the case of octave. Okay, and in the case of decade, your log of w2 minus log of w1 will be equal to 1, because log 10 is 1. So using these relations you can calculate. Okay, let that week pass. I will tell you how you can actually solve that question. Okay,
Okay, ma'am.
so the assignment period is over, the submission period is over. What is the last date of assignment submission?
It is one, ma'am.
Okay, so in the next week I will tell you how we can actually convert from octave to, so these are the hints for you. You can use these things to get your answer. Okay, this is the second question is nothing but about the corner frequencies. What are the corner frequencies? So we have just calculated. It is 1, 2 and 5. So no need to solve this again. Okay. Okay, find out the magnitude of the transfer function as frequency tends to 0. So the transfer function was, it was gs into hs was s plus 1 divided by s plus 5 into s plus 2. Okay, find out the magnitude as omega tends to 0. What will be the magnitude of g into h in dB? Okay, in the frequency domain, this will be 1 plus j omega divided by 5 plus j omega and 2 plus j omega. Okay, what is the magnitude in dB? It is 20 log magnitude of g into h. So it is 20 log. What is the magnitude of numerator? Under root 1 plus omega square, and the denominator part we can directly subtract, so it is minus 20 log 25 plus omega square and minus 20 log 4 plus omega square. Now put omega tends to 0. What will be the magnitude? It will be 20 log 1 minus 20 log 5 minus 20 log 2. So it will be minus 20 log 10. Okay, and what is minus 20 log 10? How much is log 10?
Minus 20. Locked in is 1.
1. So it is just minus 20. Okay, okay, for the same transfer function, find out the phase as frequency tends to infinity. Let me again write the transfer function for you, open loop transfer function. Okay, what is the phase of numerator? You can quickly write it. It is nothing but tan inverse omega. For denominator, it is minus tan inverse omega by 5 and minus tan inverse omega by 2. Now put omega tends to infinity. What will be the phase?
90 minus 90 minus
It
90.
is 90 minus 90 and minus 90. So we'll have minus 90 degrees. Very simple one. Okay, next we have the question. What is, okay, you got your question here. What is the slope in dB per octave of the low frequency asymptote in the magnitude plot of the sinusoidal transfer function? But here we need not to do anything, because what was the low frequency asymptote?
It is 0.
It was 0. Okay, so whether it is in octave or decade, 0 is 0, right? So it is, sorry, 0. Okay, what is the static position error constant? Do you remember static position error constant? What was that?
KPE.
Yes, KPE. And how we calculate it for the given open loop
Limit,
transfer function?
limit s tends to
Limit
0,
S.
GSHS.
Yes, so we put s tends to 0 and it is gs into hs. And gs into hs, it is already given to us. So let's put that. It is s plus 1, s plus 5 and s plus 2. Now if you put s tends to 0, it is just 1 by 10. So I think it is 0 0.1. Now sometimes what you are asked is, you need to identify the value of steady state error or kp. No, you need to find out the steady state error using the Bode plot. Okay, so in that case you need to find out the gain, okay, using the type of the system given, and then you find out the steady state error based on the given input. So here in the next question, but in this case we are already given a transfer function, so we need not to identify the transfer function from the Bode plot. But sometimes first we need to identify the transfer function from the Bode plot and then find out the value of gain k from there, and ultimately we need to figure out the static position error constant or whatever is asked in the question. Okay, so in the backward manner we can also solve this question. But here we can easily apply the formula because we have the transfer function with us. Okay, what will be the steady state error if a unit step input is given?
1
Any
upon 1
answer?
plus kpe.
Yes. So for the unit step input, the steady state error is nothing but 1 by 1 plus kp. So we had kp of 1 by 10. So it is 10 by 11. So I think it is 0.91.
Yes.
Yes. Okay. The plot of the real part of the sinusoidal transfer function and its imaginary part as frequency is varied, it is called, what is the plot?
Nyquist plot.
Nyquist plot. Okay, so what is the difference between polar plot and Nyquist plot?
Nyquist plot is a
I think
mirror
in
image.
mirror image, no, no.
Image.
Yes, yes, please. Okay, so in polar plot, what we do, in the lecture, you must have seen that we were varying frequency from 0 to infinity in most of the time. Okay, so when we vary frequency from 0 to infinity, that, and when you plot the real and imaginary part of the transfer function, you get the polar plot, right? So here omega is varied from 0 to infinity, and the plot of real and imaginary part of transfer function, if omega is varied from 0 to infinity, is the polar plot. And why we say that Nyquist plot is the polar plot plus the uh, mirror image of
Inverse
polar
plot.
plot plus some semicircle kind of thing, right?
Semicircles.
Yes, so Nyquist plot is the sum of these three. And this basically is coming because here we vary omega from minus infinity to infinity. Okay, so 0 to infinity part is already covered by polar plot, and minus infinity to infinity part is coming from the mirror image, and then extra we have this semicircle thing. Okay, so when you vary frequency from 0 to infinity only, you get the polar plot. Or in Nyquist plot, if you say that frequency is varied from 0 to infinity only, so that Nyquist plot is the polar plot, right? Okay. Which of the following statements is true about the Nyquist plot of the factor 1 by s plus 5 as the frequency is varied from 0 to infinity? So in this question, here it is explicitly mentioned the range of omega, right? It is mentioned that frequency is varied from 0 to infinity. If it was not mentioned, it was just asked what will be the Nyquist plot, then the answer will change significantly, right? So here the frequency range is mentioned. So it is varied from 0 to infinity, and you have to find out the quadrant in which the Nyquist plot will fall. The transfer function is given as 1 by s plus 5. How can we guess the quadrant? So first there are some basic blocks for which you can remember the polar plot. Like in the lectures, the professor has told you the Nyquist or the polar plot of what say, um, 1 by s block, first order time constant block, second order block, right? So for these system you can remember the basically there he has plotted the polar plot. where the frequency is varied from 0 to infinity. So for these simple blocks, you can remember the Nyquist plot. But for the learning purpose, how we draw the Nyquist plot for a given transfer function or for a given factor, like here we have 1 by s plus 5. So by seeing this, we know this is a time constant, right? It is a first order system. And for this system, if you remember from the lecture, how does the polar plot looks for this transfer function?
Semicircle in the fourth quadrant.
Yes, so it is nothing but a semicircle. Okay, so here you have 0, here you have 1, and your this frequency is 0 and this frequency is infinity. Okay, so by remembering, you can guess in what quadrant it will lie. It is the fourth quadrant. Okay, another thing, if you don't remember, because there are so many things to remember, what you can just do, you find out the magnitude. Let's say I'm calling it m, so the magnitude of m will be, so this I can write as 5 plus j omega, right? And if I divide and multiply with 5 plus j omega, numerator and denominator, it will give you 5 minus j omega. So basically I am uh, separating the real and imaginary part of this transfer function. So it is 25 plus omega square. Okay, so real part of m, it will be 5 plus 25 plus omega square, and imaginary part of m will be minus omega by 25 plus omega square, right? Now in Nyquist plot, we know we plot real part of m and imaginary part of m by varying the frequency omega. Now if you vary omega, what will be the real part? Will it be positive or negative or what? We have 5 plus 25 plus omega square. Is it a positive number always or a negative number always, or both of it? So it is always going to be a positive number. So the real part is always
Yes,
going to be positive number. And what about the imaginary part? If you vary omega from 0 to infinity, that is your omega is positive always, then this imaginary part will be always negative because you have minus
negative
here.
always.
Okay, so for every omega, your real part is going to be positive and your imaginary part is going to be negative. So which quadrant has this property? It is the fourth quadrant, because here in fourth quadrant you have real part always positive and imaginary part always negative. Okay, so if you have a very complex type of transfer function given and you are asked to find out in which quadrant it will lie, you just separate out the real imaginary part and you can guess whether it is going to lie. Or also you can find the magnitude and phase, from there also you can guess. Okay, but the most easy way is to separate into real and imaginary part, because here you can easily guess about the quadrants.
Can such question ask in gate math?
It can be asked, you never know. It can be asked, but it not in this simple manner. It can be twisted.
Okay, ma'am.
Okay, now you are varying the frequency from 0 to infinity. Okay, like we have done in the previous problem for the same transfer function. What will be the radius of this semicircle? What will be the radius? Okay, at omega equals to 0, if you put omega equals to 0, what will be the real and imaginary part?
The real part is 1 by 5 and imaginary part is 0.
Point 2.
Okay, so real part is 5 by 25, it will be 1 by 5, and imaginary is 0. Okay, so you have the semicircle, and this value, that is this diameter, is of 1 by 5. Okay, then what will be the radius?
0.1.
Point 1.
The half of it, that is 1 by 10. Okay, so radius will be half of 1 by 5, that is 1 by 10, so it is point 1. Okay. Okay, find out the Nyquist plot of e to the power minus 5s, and it is given that its Nyquist plot is a circle. What is the radius of this circle? Okay, so for this transfer function, if I say it is e to the power minus 5s, what can I write for it in frequency domain? We have to replace s with j omega. It is e to the power minus j 5 omega, right? Now what will be e to the power minus j of something? What is e to the power minus j theta in terms of cos and sine?
Cos theta. Cos theta minus j sine
Cos
theta.
theta minus j sine theta. Okay, so this is nothing but cos 5 omega minus j sine of 5 omega. Now if you find out its magnitude, what will be the magnitude of e to the power minus 5s?
Under root of cos square 5 omega plus sin square 5 omega.
Yes, it will be cos square 5 omega plus sine square 5 omega. And what is cos square plus sine square?
1, ma'am.
1.
It is going to be 1. So from here you figured out the magnitude of e to the power minus 5s is always 1. And you're already given that you are given a circle, means the Nyquist plot of e to the power minus 5s is a circle. Okay, it is given that the Nyquist plot is a circle, and from here we have calculated what is the magnitude. So always you have a magnitude of 1. So what is the radius of this circle?
How circle, ma'am?
It is already given. So for in this case, if you see, what is the magnitude of e to the minus 5 is? It is 1. So what pattern you can draw on your real and imaginary plot where you get a constant magnitude kind of plot? You have two options. You can have a, a point where this magnitude is always 1 whatever the frequency is, okay, and the second option you have is you can have a circle, because circle has a fixed radius, that means a fixed magnitude. So you can either have this option or this option. Okay, now in order to pick the um, correct option, you calculate the phase of e to the power minus 5s. What is the phase of e to the minus 5s? It is tan inverse of minus sine 5 omega by cos 5 omega. Then what is it? Tan inverse of minus tan 5 omega. So that means it is 5 omega, right? So from here,
Yes, ma'am.
what does it mean? Its phase is always going to vary with respect to omega. It is not going to be fixed. So the first option can never be the case, because if we have a point here, then the magnitude is fixed, that is of 1, but that is the magnitude we calculate with respect to the origin. It is 1, but its phase is always 0, right? If you calculate the angle with respect to the x-axis, it is always going to be 0, but here what we are getting, our phase is going to vary with respect to omega. So that is only possible with the option number 2. Okay, so you start from here and you keep on circling, 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 right? So this is omega equals to 0, and again you land up here with omega equals to infinity. And what is the radius of this circle? Just the magnitude, and magnitude is 1. Okay,
Yes, ma'am.
okay, now for similar type of question, now we have a second order system, and the frequency again is varied from 0 to infinity. So you can see here that although it is mentioned Nyquist plot, but at that moment they have mentioned the frequency range also, so that ultimately becomes the polar plot. So for this second order system, find out the quadrant where the Nyquist plot will lie for omega varying from 0 to infinity. So one way is that you remember the Nyquist plot or the polar plot of second order system, or you can separate the real and imaginary parts, and then you can guess the uh, quadrant in which this going to lie. So you can follow these two any approaches. So anybody remember what is the polar plot of second order transfer function or second order system? So it is going to be something like this. Okay, so this is going to be,
It is, ma'am, half cardioid.
sorry,
Cardioid-like structure. Cardioid.
yes, yes. So this is how the Nyquist the plot, if omega is varied from 0 to infinity, is going to look like. So in which quadrant it is lying? So it is third and fourth quadrant.
third and fourth quadrant.
Okay. Now can you identify which frequency is this? At which frequency it intersects the imaginary axis?
Omega equal to omega n.
Yes, so this frequency is omega equals to omega n. And what will be the resonant frequency for this case? So we know at the resonant frequency, if you are given a sinusoidal input, the at resonant frequency, you will get the maximum amplitude, right? So if you correctly draw it, the frequency at which you get the maximum amplitude or the maximum magnitude, that gives you the resonant frequency. Okay, if you want to check out the quadrant by separating the real and imaginary part, from that way you can also do that. So I have calculated it. Yes. So for this case, if you find out the real part, it will be 8 minus omega square divided by 8 minus omega square whole square plus 16 omega square, and your imaginary part will be minus 4 omega, same denominator. Okay, now from here you can also see that if you vary omega from 0 to infinity, your imaginary part is always going to be negative, right? And what about the real part? So the real part will be positive when omega square is less than 8. Okay, your real part will going to be positive, and for omega square greater than 8, your real part is going to be negative. Okay, so there is a transition at omega equals to under root 8, and this is also verified from here at omega equals to under root 8, which is nothing but the natural frequency, right? So from here also you can conclude the same thing. So if you have any confusion in remembering where and how your Nyquist plot is going to look like, or in which quadrant is going to lie, you can just calculate the real and imaginary part and just look on the sign of it by varying the omega. That gives you the exactly same answer.
Ma'am, can we find resonant frequency also?
For resonant frequency, you are given the input. And for this case, I don't know how to calculate. I haven't seen in the question like that. So for that, what you can do, you you calculate the magnitude, okay, and you equate, and you how can you calculate this?
Maximizing the magnitude,
Yeah, maximum of the magnitude, but what will be the maxima?
it will be, I think, calculated by differentiation and all.
By putting derivative with respect to omega equals to 0, right? I think we can do that like this. So you can find the derivative with respect to omega
Okay, okay, ma'am.
of the magnitude, put that to 0, and I think that omega will give you the horizontal frequency.
Okay, ma'am.
Fine. Now in this question for s plus 2 divided by s plus 5, what we need to find out? The radius of the semicircle. Find out the radius of the semicircle. Now for this type of question, whatever we have remembered, all things fail, because here we have numerator by denominator type of thing, and no any type of transfer function that we have calculated or we have plotted the Nyquist plot will be used here. So for such type of problems, we explicitly have to find out the real and imaginary part by varying the omega, or the magnitude and phase by varying the omega, and then observe the plot and then find out the radius. You are given s plus 2 divided by s plus 5. Okay, in frequency domain it is j omega plus 2, j omega plus 5. Okay, how can we separate out the real and imaginary parts? Cross multiplication we can do. So it is j omega minus 5 and j omega minus 5. What will be denominator? Right? And what will be the denominator? It will be minus omega square and minus 5 minus 3 j omega and then minus 10. So all the minus will cancel out. So omega square plus 10 divided by omega square plus 25 plus j 3 omega divided by omega square plus 25. Okay.
And in denominator, it will be only plus omega square minus 25.
Yeah, it will be, but I have taken j omega plus 5 and j omega minus 5. You must have taken 5 minus j omega. I have taken j omega minus 5. So anyway, ultimately all the minus will cancel out and you will get this.
No, ma'am, j first term square j omega square will be positive j omega square.
Yes. Okay, let me show you what I am talking. So you have done this 5 minus j omega, right? You have used the factor
Yes,
5 minus j omega, right?
yes,
So in that case, you will have 25 plus omega square, okay? And in denominator, sorry, numerator, you will have omega square
yes.
plus
Ma'am,
3j
yes,
omega
understood, understood.
plus 10. So both of them are same,
Yes, yes.
okay? Okay, now we have the real and imaginary part in with respect to omega. We can form our table. What happened? Yes. So let's, so this is the real part and this is the imaginary part. Tell me what will be the real part at omega equals to 0.
It will be
10 by 25. So we can write it as 0
0
0.4.
.4.
And j imaginary part is 0. What about omega tends to infinity? So if omega is
Real
very
part
large,
infinity.
this will be omega square by omega square, that is 1, right? And this will be 3 by omega, we can approximate, so it will be 0 again. Now let's see how our Nyquist will look. So this is the real part, this is the imaginary part. At omega equals to infinity, we have imaginary part as 0 and real part as 0.4. So this is 0.4 comma 0, and this point is omega equals to 0. And as omega infinity, we have real part as 1. Okay, so in that case, let me extend it here. So this is 0.4 comma 0 at omega equals to 0, and this is 1 comma 0 at omega tends to infinity. And it is given that we have a semicircle, so the circle can go like this or can go like this. Now if you see the imaginary part, if omega is varied from 0 to infinity, the imaginary part is also always going to be positive. So the semicircle will form like this because we have to keep the imaginary part as positive. Now since you have the semicircle and you have the end points, can you calculate the radius of the semicircle? What will be this midpoint?
Point 3.
Will be 1 plus 0.4 by 2, that is 0.7. So this point is 0.7 comma 0. Now the radius will be 0.3. Okay, any doubt?
No, ma'am.
Okay, yes. Okay, in the previous problem, find out the phase of the sinusoidal transfer function. Okay, find out the frequency at which the phase is maximum. At which frequency this phase will be maximum? Okay, let's first,
Tangent to the semicircle, ma'am.
yes, correct. Calculate the angle which makes the tangent to the point. So this is how it looked. Okay, so assume this is a semicircle and we have 0.4, we have 1, and this is 0.7. Now your maximum phase will be the point at which you have a tangent from the origin. So let's draw the tangent. So we get the tangent here, right? And this makes 90 degree. Then what will be this angle theta?
First, we consider sine of angle theta.
Why can't we directly calculate tan theta? We have all the terms with us. So this part is radius, and what is the radius? It is 0.3. And what will be what will be tan theta? Tan theta is 0.3 divided by, this is 0.7, so this is 3 by 7. Okay, now we just have to put this to our transfer function. So our transfer function was s plus 2 by s plus 5. So its phase is
Ma'am, opposite
tan,
of adjacent is sin theta, ma'am.
sorry,
Opposite upon hypotenuse is sin theta, ma'am.
you can calculate the sine also, and from sine, so if you want to calculate the sine theta, so sine theta will be what? Perpendicular. So this is perpendicular by hypotenuse. This. So your right angle triangle is this, and hypotenuse is this. Okay, okay. Sorry, sorry. Yes, yes. Sorry. So this is sine theta. This is sine theta. Because for tan theta you need to know this, right? So it
That's
will be
what
zero
I
point
see.
0.3 by b if you want to. So this also you can calculate if you want. That will be just under root of zero point 0.7 square minus zero point 0.3 square. Okay, so what will be theta?
25.37.
How much? 23 point?
It is 25.37.
I have not calculated it, so whatever you are saying, I think it is correct. It is
37.
25.37 degree. Okay,
Yes.
what will be tan theta? Tan of
0.47.
25.47. Okay.
47.
And what was our transfer function? It was, now ultimately we have to find omega. It is s plus 2 by s plus 5. So it was s plus 2 by s plus 5. So this phase was tan inverse omega by 2 minus tan inverse omega by 5. No need to do this. We can do this with the real and imaginary part only. That will be more easy. Okay, so what is tan theta? Tan theta is real part divided by, sorry, imaginary part divided by real part, and and your imaginary part is what? 3 omega divided by omega square plus 25, and your real part is omega square plus 10 omega square plus 25. So it is 3 omega by 10 plus omega square equals to 0.47. From here you can calculate omega. Okay, I have not calculated it. Please calculate it. The correct answer for this is 3.16. So if you calculate it, you will get omega equals to 3.16 radian per second. Okay. Please check if you are getting this value by calculating omega from here.
Just once, 1 minute. 3.62 and 2.76. Two values are coming.
3.62 and 2.76.
Yes.
Okay. Okay, so the nearest value which is close to the option is 3.16. Maybe the angle you have calculated, maybe there will be some other figures here, 4, 5 or 6 something. So that's why you are not getting the
Yes,
exact
yes.
answer. So if you take the angle precisely, you will get 3.16, I guess. Okay. Okay, now for the same question, no, not for the same question. Here we have, earlier we had s plus 2 by s plus 5. Okay, so now you can easily tell me for this transfer function or for this system, where will the Nyquist plot will lie. We have just plotted the Nyquist for this one. What was the quadrant? In which quadrant the semicircle is lying?
First quadrant.
First quadrant, so no need to solve anything. We have already calculated everything for this. Okay, now let's solve some other problems because we have time. Okay, so let's start some questions. Okay, so the question is, the transfer function is given by V out by V in is 1 minus s divided by 1 plus s. So these are some questions related to Bode plot, or maybe I have some question on Nyquist also. Let the output of the system be V naught t equals to Vm sine omega t plus phi for V input, which is a sinusoidal with magnitude Bm and frequency omega. then the minimum and maximum value of phase or phi in radian. You are given a transfer function, and for this system you are applying a sinusoidal input which is Vm sin omega t, and what you observe is that the output remains with same magnitude, but the phase is shifted by angle phi. So that's what we observe in case of sinusoidal input given to an LTI system. The magnitude is scaled by the magnitude of input, and the phase is shifted by the phase of the transfer function at the input frequency. Okay, so for this system you have to calculate the minimum and maximum value of the phase.
Yes, ma'am.
Okay, so again this is a very simple question, but it is given in such a way that the reader may get confused as if what is asked, but this is very basic. You just have to find out the phase and tell me what is the maximum phase and minimum phase. So let's call this transfer function as g of s, which is 1 minus s divided by 1 plus s. Okay, so what is g in frequency domain? It is 1 minus j omega by 1 plus j omega. So what is the phase? It is minus tan inverse omega and minus tan inverse omega, which is minus 2 tan inverse omega. Okay, now you are varying omega from, let's suppose in Bode plot you are varying from almost 0 to almost infinity, right? You are varying omega like that. So what will be the maximum and minimum phase of g? So that you can easily calculate if you remember the plot of tan inverse. What is the plot? How is the plot of tan inverse? So if I want to, so this is how the plot of tan inverse looks like. So it is, as omega tends to infinity, it is 90 degree. If it tends to minus infinity, it is minus 90 degree. Now we are given minus 2 tan inverse omega. So how will be, so this is for tan inverse omega. What will be for minus tan inverse omega? Just the mirror image. Okay, so it will be like this for minus tan inverse omega. Okay, and now you have scaled it by 2. So in place of 90 it will be 180 degree and it will be minus 180 degree. Okay, now omega is varied from, let's suppose, 0 to infinity. Okay, because in real systems we have Omega varied from 0 to infinity. Then what is the minimum phase we have? What is the minimum phase? So this is your plot of this function. What is the minimum value?
Plus 180.
Minus 180. And what is the maximum value?
Positive 180.
No, remember that. So that's, you may do mistake. So you are varying omega from 0 to infinity, not from minus infinity to infinity. So this is the value at omega equals to 0, and this is the value as omega tends to infinity. So as omega is 0, what is the phase?
It is 0.
0. So the maximum phase that we can have is 0 degree, and the minimum phase that we can have is minus 180 degree. This part we don't consider because we discuss frequency, positive frequencies, not negative frequencies. So our region of interest is just when omega is varied from 0 to infinity. Okay.
Yes, ma'am. How draw this graph, ma'am?
So you remember the graph of tan inverse. So this is a plot of tan inverse. So at 0 we have 0, at 45 degrees we have 1, at 90 degrees we have infinity,
Yes,
right?
yes, yes, yes.
And then,
Rotated.
yes, so for minus tan inverse it will be mirror imaged, and for 2 of tan inverse it will be double of that. So that's how we have
Yes.
drawn it. Okay, so let's move to second, another question. Another question. Yes, the Bode plot for transfer function g of s is shown below. So how is the transfer function? It is, sorry, how is the Bode plot? It is like this. So this is omega 1, this is 10, this is 100, this value is 32, okay, this is 20, and this is 0. Okay, so it is starting from 32 and crossing the 0 dB line, and this value is minus 8. So okay, so 1 here means at omega equals to 1 you have magnitude of 32 dB, right? So this is for frequencies. Okay, so this is how the magnitude plot of Bode plot looks like. Find out the transfer function. Find g of s.
will be 1 upon S type.
1 upon S type, you have to give me the exact transfer function. Whether 1 by S, 1 by S square, 1 by S cube, K by S, or K by S plus 2, something. First, tell me what is the slope of this line, because so this is going beyond, so we have no corner frequency here, right? So there will be no time constant type of thing, so that is for sure. So the transfer function will be of the type k by s, k by s square, k by s cube, right? Because what we can observe is we have a negative slope, but the slope magnitude we don't know. It is a negative slope and we don't have any corner frequency, means there will be no st plus 1 type of block, right? And we have no positive slope, means there is no zero in the system. So the only option that we are left with is of the form k by s or k by s square or k by s cube. So, and
Slope is
this
4
slope is
minus 4.
minus
4.
minus 4. Okay, let's see what is the slope. So how we calculate slope for any graph? What is the slope?
Y2 minus Y1 upon
Yes,
X2 minus X1.
so let's give this as x2 y2 and give this point as x1 y1. Okay, what is y2? It is minus 8 and y1 is 32. Okay, and we have log of x2 minus log of x1, because here we have a logarithmic scale in the x-axis. So numerator is minus 40 and this is log 10 minus log 1, because at 1 it is given that we have magnitude 32 dB and at 10 it is given that we have magnitude of minus 8. So it is minus 40 dB, and you can observe here that this denominator is nothing but decayed, because here we have frequency 1, here we have frequency 10, so it is
Minus
10
40
times
is
of, yes, so this is minus 40 dB per decade. Now minus 40 dB per decade means we have how
2
many
poles at origin.
poles? Yes, so it is type 0, type 1 or type 2 system.
Type 2 system.
So it is a type 2 system. So one thing we are sure about is that the transfer function will be of the form k by s square. Now can you find out k? So for to find out the value k, you are given the value at omega equals to 1. So just find out magnitude by putting omega equals to 1, then you can get the value of k. So if you find out the magnitude of g, it will be log, sorry, 20 log k, it will be 20 log k minus 20 log omega square. Okay, so it is 20 log k minus 40 log omega, and this value at omega equals to 1, it is given that this magnitude is how much? 32. This 32. So 20 log k at omega equals to 1, it is given 32. So minus, sorry, excuse me, minus 40 log 1, it is given as 32. And log 1 is 0. So 20 log k is 32. So log k is, if you calculate, it will be 1.6. So k is 10 to the power 1.6. What will be k? How much is 10 to the power 1.6?
39.81.
So it is 39.8. So what is your final transfer function? It is 39, sorry, 39.8 divided by s square. Okay.
Ma'am, is omega square because we have 1 by s square now.
Sorry, what? What you are asking?
We, we use omega square.
Here,
What is the reason?
that is the reason for what? Ask again, I didn't get your question.
If we had 1 by s cube term, then we can use omega cube there.
Yes. If you had like a k by s cube, in that case, if you had the slope of minus 60 dB per decade, then you
Okay,
would
clear,
have k by s cube, and in that case, you would have used omega cube here.
clear, ma'am.
Okay. Okay, let's solve some more problems. Oh, yes, that's an interesting question. So you are given, okay, so you are given Nyquist plot for omega 0 to infinity of transfer function g1s and transfer function g2s. Okay, and how their Nyquist plot looks like. So this is like, so the Nyquist is this blue part. Okay, and this is extending from minus infinity, and this value is at omega 0, and here the value is infinity. And similarly, you have another transfer function whose Nyquist is just the mirror image. Okay, so it is extending to infinity, and this is omega at 0, and this is omega at infinity. Okay, so this is the real part and this is the imaginary part. So you have two transfer function g1 and g2, and their Nyquist plot is given to you for omega varying from 0 to infinity. What will be the Nyquist plot for g3 of s, which is equal to g1s into g2s? Okay, as omega varies from 0 to infinity. Okay, for g1 and g2, the Nyquist is given to you. You have to find out how the Nyquist will look for g3, which is the multiplication of these two transfer functions. Now, can you guess the transfer function of G1s by looking at the Nyquist plot? For this Nyquist plot, you have real part as 0.
1 by s, ma'am.
Yes. So this is just the simplest one, and this you should remember always. So this is the Nyquist of 1 by s. Okay. And the Nyquist of, and what is the transfer function of G2s?
Nyquist of s.
Simple, the Nyquist of s, because for this the imaginary part is always negative, and for this the imaginary part is always positive for omega varying from 0 to infinity. From this you can also guess whose transfer function will be what. Okay. Now if you calculate, so there were options where different type of graph were given. So one graph was like a circle, another graph was like uh, a point at the origin, and another graph was like a point at real part 1, and there was another option, I don't remember that. Now if you find out g1 into g2, what will be the transfer function? It is nothing but 1, because 1 by s into s is just 1. So what is the real part of g1 into g2? It is 1.
Ma'am.
And what is the imaginary part? It is 0. We have no
0.
imaginary part. Okay, so either option 2 or option 3, option C is correct. Okay, because in the first option we are getting imaginary part also. So this is not the correct option. Second and third can be correct. Now from here we are getting real part as 1 always. Okay, so this option also goes out. So the correct option is this, because we have real part as 1, and this Nyquist plot is just a constant point. There is no variation in it, because its transfer function is constant. There is no frequency components. So it doesn't matter how we vary the frequency, the Nyquist plot remains the same. It is a constant.
Yes, ma'am.
Okay, let's solve one last question we can solve. Okay. A system with transfer function given as g of s equals to s square plus 9 s plus 2 divided by s plus 1 s plus 3 s plus 4 is excited by sine omega t. The steady state output of the system is 0 at omega equals 2. You have to find out the frequency at which the steady state output of this system is 0. And you are exciting this system with a sinusoidal input.
How to proceed, ma'am?
Okay, so if you remember, if you give a sinusoidal input to the system, how the magnitude of the system is affected? Because in the question we are asked the steady state output of the system is 0.
Cannot remember, ma'am.
So the magnitude is nothing but the magnitude of the input. So the magnitude of input is 1. Okay, we have 1 multiplied here, right? There is no another gain. This is just 1 sine omega t. Okay, so that means the steady state output will be 0 only when the magnitude of this transfer function will be 0. And at which frequency the magnitude of this transfer function will be 0? So first find out the magnitude of transfer function. Okay, and then from there try to calculate the frequency at which that magnitude will be 0, because for a sinusoidal input the magnitude when the magnitude will be 0, then only the steady state output will be 0. So what does this mean is that if you plot the response or magnitude of g of s, or the time response, maybe you can say, so let's call it as yt. If you plot, so your response will start from some value. Okay, or with respect to omega I want to show you, so let's draw it like this.
Ma'am, please tell how to find omega.
Yes, I just want to picturize what I am going to. Okay, let's first calculate the magnitude of g of s. How can we calculate it?
Put s is equal to j omega.
Yes, so it will be j omega square plus 9. So first I am just calculating g of j omega. J omega plus 2, j omega plus 1, j omega plus 3, and j omega plus 4. And what will be the magnitude then? It will be
Under root of
under root of j omega square. Okay,
plus
so
9.
that's the twist here. That's the twist here. So if you expand j omega square, what it will be?
J omega into j omega
So that will be minus omega square.
minus omega square.
Yes, it will be minus omega square plus 9.
It
And
will be in under root, ma'am.
yes,
It,
yes,
yeah.
yes, you are guessing it correctly, I think. Okay, so if you have a system, an LTI system, and you are providing an input A sine omega t, what is the response of the system? The magnitude.
This will plus 5.
So if it is GS, then it will be G at omega magnitude, that is this frequency, and sine of omega t plus phi, and this phi is the angle of G of j omega at omega at this frequency, right? Okay. So the only way that this response is going to be zero, steady state means as t goes to infinity, or as the response settles down, because this is the response at steady state. This is the steady state response always. This is not the transient response, this is the steady state response. So this response will be zero only when the magnitude of g of omega, that is the omega of the input, and the magnitude of g calculated at this frequency is 0. Okay, so that's the only possible way where we have this response equals to 0, correct? So that's why I asked you to calculate the magnitude of g of j omega, right? And when you calculate the magnitude of g of j omega, so first let's calculate now. So this was just g of j omega, and its magnitude, it will be 9 minus omega square under root of 4 plus omega square, because we have no imaginary term here. So this magnitude will remain 9 minus omega square divided by 1 plus omega square, 9 plus omega square, 16 plus omega square. When this magnitude will be 0, there is only one possible way. This is a positive term, this is a positive term, this is a positive term, this is a positive term. When this factor will be 0 at omega square equals to 9. So
Omega is equal to 3.
when omega square equals to 9, this g of j omega will be 0, correct? Okay, so which frequency, if I provide the steady
3
state
radian
will
per
be
second.
0
3 radian per second.
at omega equals to 3 radian per second. So if I provide input sine of 3t, then your steady state output will be 0. Okay, so this is what is asked in this question.
Yes, ma'am.
Okay, I have one more question. If you want, I can give you as a homework, you can try. So let's give that question as a homework to you, because I think in next question, next session we have Nyquist plot, and I think in Nyquist plot we have some compensator design. So let's finish the Bode plot. Sorry, where is it? Yeah. Okay. So let's finish Bode plot in this turn only. So I have one last question for you. The asymptotic, you can try to solve this question, otherwise we can discuss it in the next section. The uh, asymptotic approximation of the log magnitude versus frequency plot of a minimum phase system with real poles and 1 0 is shown. Find the transfer function. And the Bode plot is like this. Magnitude plot we are given. We have frequency at 0.1, 2, 5 and 25, and at omega equals to 0.1 the magnitude is 54. Okay, from here to here we have a slope of, so let's first draw it, then I will tell you the slope. Okay. Okay, so these are the corner frequencies. This slope is minus 40 dB, minus 40 dB per decade. This slope is minus 60 dB per decade. This one is again minus 40 dB per decade. And this is minus 60 dB per decade, so on. So at high frequency you have a slope of minus 60 dB per decade. So for this Bode plot, try to find out the transfer function, and if you get any problem in solving it, we can discuss it in the next session. And let this week pass, we will discuss that dB per decade and dB per octave, which is asked in the assignment, in the next session, if you're not able to solve it. Okay, any other doubt?
Ma'am, is there any MATLAB session in the last?
Yeah, we can arrange for one because we may have one extra session when these 12 weeks of tutorial session are over. We can have one session where we can discuss MATLAB problems, and there we can see how to plot these Bode plots, Nyquist plot, or how to get the time response, how to calculate the poles and zeros, the Bode plot, the time response, all these things we can see.
Ma'am, will it be and using free online MATLAB.
Okay, yes, we can do that with the online version, because sometimes what happens that online version doesn't work properly. It sometimes gets stuck. So if you're able to download the offline version, then that will be okay. Otherwise, we can do with the online version also.
Our college has one paid version of MATLAB, but they don't provide to every student.
Okay, so then we can have with the online version also. There is no problem. But the only problem that I feel is that it sometimes gets stuck and it is sometimes very slow. So I avoid that.
Okay, ma'am.
Apart from this, if you have any doubt, you can ask, or let's meet in the next week to solve some more problems. Okay, thank you.
Okay, ma'am.